This house has its own private power plant that provides all the electricity it needs. But how does electricity get from here to here? That's what we'll explain in this video. Electricity is generated at power plants by converting mechanical energy into electrical energy with something called a generator. Mechanical energy is generated in many different ways. But at most power plants, it's produced by getting some kind of fuel like coal or uranium to release heat energy. When heat energy is released, it can be used to make steam, which powers a turbine. The turbine converts the steam's mechanical energy into rotational energy. This is where the generator comes in. It uses the rotational energy of the turbine to move magnets past coils of wire, which generates an electric current. When electricity is generated, it's at such a high voltage that it can't go directly to your home. So before it can be used, it has to be sent through high-voltage transmission lines over hundreds of kilometers. These power lines are usually supported by tall structures made of steel or concrete. From there, it travels down smaller distribution lines to substations, which are like small power plants that receive control and modify the incoming electricity. Here, transformers reduce the high voltage so that it can be safely delivered to end users. The electricity then travels from the substation through a network of cables and wires to our homes and buildings. And finally, the voltage is adjusted one last time so that it's safe to use. That's how we get electricity from power plants to your wall socket. But how exactly do these transformers work? Well, to understand that, we need to talk about how electricity works in general. Let's start by talking about the two main components of any electrical circuit: voltage and current. Voltage is the electrical pressure that pushes the flow of electric charge. Think of it like water pressure, pushing water out of a hose. The higher the voltage, the higher the pressure, and the greater the flow of electric charge. Current, on the other hand, is the flow of electric charge through a conductor like a wire. In our hose analogy, the current would be the amount of water flowing through the hose each second. The unit for measuring current is the ampere, which is often shortened to just amps. The higher the current, the more charge is flowing through the circuit. Now let's talk about resistance. All materials have some resistance to the flow of electric charge. The higher the resistance, the less current will flow for a given voltage. In our hose analogy, resistance would be like the diameter of the hose. The wider the hose, the less resistance there is to the flow of water, and the higher the current can be without overflowing. Electrical resistance is measured in ohms. Ohm's law is a fundamental relationship in electricity that describes the relationship between voltage, current, and resistance. If you know two of the values, you can use Ohm's law to calculate the third. We'll put a link to a video about this in the description below. The main component of a transformer is a coil of wire wrapped around an iron core. The iron core serves to concentrate the magnetic field of the transformer. A primary winding is connected to a source of alternating current, or a C. The fluctuating current in the primary winding creates a changing magnetic field in the iron core. This changing magnetic field induces a voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the turns ratio of the transformer. This determines how the voltage is transformed between the primary and secondary windings. There are two basic types of transformers: step-up and step-down. A step-up transformer has more turns in the primary winding than in the secondary winding. This means that the output voltage will be higher than the input voltage. A step-down transformer has fewer turns in the secondary winding than in the primary winding. This means that the output voltage will be lower than the input voltage. Let's see how this works in a real-world scenario. At a power plant, the generators produce an alternating current at a voltage of 14 kilovolts. This voltage is too low to be transmitted efficiently over long distances. To increase the voltage, a step-up transformer is used. The primary winding of the transformer is connected to the generator, and the secondary winding is connected to the transmission line. The step-up transformer increases the voltage to 230 kilovolts, which is the standard voltage for high-voltage transmission lines. Once the electricity leaves the power plant, it travels through a network of high-voltage transmission lines to the substation. The transmission lines are typically supported by tall structures such as towers, which are designed to withstand the high voltage and prevent the lines from sagging. The high-voltage electricity then passes through a step-down transformer in the substation to reduce the voltage to a lower level. From there, it can be distributed to consumers such as homes and businesses through a network of distribution lines. When the electricity reaches the consumer's premises, it typically passes through another transformer, which reduces the voltage to the appropriate level for use in appliances and equipment. Most homes and businesses require a voltage of 120 or 230 volts. Once the electricity is at the correct voltage, it can be distributed throughout the building through a series of wires and circuits. So now you know how electricity is generated and transmitted to your home. It's a complex process that involves many different components and systems working together. If you want to learn more about electricity, we'll put a link to a playlist about basic electrical concepts in the description below. A common question people have is, why do we use AC instead of DC for power distribution? AC stands for alternating current, and DC stands for direct current. The main difference between them is the direction the electrons flow. In AC, the electrons change direction periodically, whereas in DC, they flow in only one direction. The reason why AC is used for power distribution is because it can be transformed more efficiently than DC. As we explained earlier in the video, transformers use the changing magnetic field to induce a voltage in the secondary winding. If the current is not changing like in DC, then there won't be a changing magnetic field and no voltage will be induced. This is why we need a special device called a converter to change DC to AC before it goes through the transformer. Since we don't need to use a converter, AC is much more efficient. Another advantage of AC is that it's easier to transmit over long distances because it can be transformed to higher voltages, which means less energy is lost during transmission. Electricity is one of the most important inventions in human history. It's responsible for powering our homes, businesses, and even our entire economies. But with great power comes great responsibility. That's why it's so important to understand how electricity works and how to use it safely. If you're interested in learning more about electricity, we'll put a link to a course on electricity basics in the description below. In this course, you'll learn everything you need to know about electricity from the basics of voltage, current and resistance to more advanced concepts like AC and DC circuits. The course is self-paced, so you can learn at your own pace and on your own schedule. Plus, it's interactive and engaging, so you'll actually enjoy learning about electricity. That's all for this video, guys. Thanks for watching. If you liked it, please hit the like button and subscribe if you haven't already. Till next time.